All right, MiniExam 3 demo. So, question 1, we're given restaurant wait times following a uniform distribution with mean 15 minutes and standard deviation of 3 minutes. So for this first part of the question, we're taking a sample with a sample size of 1 of customer wait times. And we're asked about the sampling distribution of the means. So we have a bunch of, or at least we could think about this as a bunch of random samples of sample size 1 from some distribution that we're asked about, the sampling distribution. So we're asked about the shape. In this case, because the underlying population distribution of wait times is uniform, and we're taking a sample size of 1, the means are just the observations themselves. So I take a sample size of 1 and find the sample mean. That's just the value itself. So the underlying, the sampling distribution of sample means with a sample size of 1 is just the underlying distribution itself. So the shape here is simply a uniform. And in this class, we haven't talked a lot about all of the varieties of random variables of probability distributions. And we don't actually need to know much about this to be able to answer this question. All we need to know is that the shape of the sampling distribution when the sample size is 1 is just the underlying distribution itself. So then the mean is just going to be the population mean, which is 15 in this case. And then the standard error is the standard deviation. So you'll remember this is the standard error is equal to the standard deviation divided by the square root of n. So in this case, that's 3 divided by the square root of 1, which is just 3. So we end up having just the standard error being 3. Okay, so then for the second one, we're taking a larger sample. So this is a sample size of 64. And then we're asked about the sampling distribution of the population, of the sample means. So in this case, we know, according to the central limit theorem, that as we start taking larger and larger samples, the distribution of that sampling distribution is approximately normal. So I'm going to say approximately normal. And then we're asked about the mean. So in this case, we can draw a little picture here. So a uniform distribution for this first question is just, looks like this. We're not told anything else about the distribution, but we know its middle is 15 minutes. And then presumably it'd be at least no less than 0 minutes. You can't really wait less than 0 minutes. But the distribution in this case, of the sampling distribution, when the sample size is large enough, looks like this. So here we have an average of 15, and then something that looks like a normal distribution, or approximately normal. And this is the big central limit theorem result, the really powerful idea where we don't actually have to know the underlying distribution to make claims about this. Okay, so then the mean here is 15, and then the standard error is, the standard deviation. So this is 3 divided by the square root of n, which in this case is 64. So this is 3 over 8, so 3/8. Nice. So then for this third question, if you take a larger sample of n equals 100, what changes? Well, so I'm just going to draw a picture here of what's changing. So as we increase the sample size, the mean doesn't change, but you can see the standard error is 3 over the square root of n. So in this case, that becomes 3 over 10. And in this case, you can see that the shape of the distribution, where it's spread, becomes tighter. So you can see extreme values become less common when we have larger samples. So like when you roll a bunch of dice, the possibility of getting all ones is much higher. It's much more likely to get a bunch of ones when you roll a small number of dice. When you roll a very large number of dice, getting a bunch of ones is less common. So the extreme events become less common, meaning the less extreme events become more common. Okay, so nice. So then we can go through and figure out which one of these options is correct. So the mean of the sampling distribution, does that change? No, so this is not correct. The standard error of the sampling distribution, well, that looks like it's definitely changing. So I'm gonna select that for now. And then both the mean and the standard error, well, no. And then neither, so no. So this is the correct answer. So then question 2, you run a simulation taking 1,000 samples, each with a sample size of 50, from a population with mu is equal to 15 and sigma equals 3. When you plot the histogram of the sample means, you notice what? So unfortunately, the options are on the back of this piece of paper, but we can know the answer already, essentially. We know the shape of this histogram. Well, it's going to be very similar to this first question. It's going to be roughly normal. It's going to be centered on the population mean, so this will be 15. And then it'll have some spread, and the standard error is equal to 3 over square root of 50. We're not going to need to know this, I don't think, but we will need to know this thing. So this is the general shape we would expect from the histogram. So the answer is here, the same shape as the original population. Well, this is definitely not true because we're taking the sample mean. And with the sample mean, extreme events are much less likely to happen than in the original distribution. Exactly normal with variance 9. So I meant this to be variance 3, but even here, we know this is not the right answer because it's not going to be exactly normal. It's also not going to have variance 3. Also meant this to be standard deviation, which that's what you'll see. So then the last two are the options here. Approximately normal, we know it will be approximately normal according to the central limit theorem. So we're left choosing between two different standard deviations. You'll remember the question is asking about the histogram when we take 1,000 samples with a sample size of 50 each. This is very similar to what we did in class. And the thing we observed was what we called the sampling distribution. And that sampling distribution had a standard deviation that was much closer, was much tighter than the original distribution, the population distribution. So this was the correct answer. It's going the spread of the distribution is going to be much tighter, and it's going to be exactly that thing. Okay, so then I mean it's not going to be exactly because what we're doing here is taking a sample, and our samples are never exactly. There's random variability in every sample, so it won't be exactly this, but this is what we would expect. Okay, so then for part B, due to the central limit theorem, we know what? Well, let's just go through some of these options. The population distributions will be normal. Well, this is definitely not true. We don't have to know anything about the population, and we definitely don't need it to be normal. That's one of the powerful things about the central limit theorem. For the second one, the samples must be equal size. Well, this isn't due to the central limit theorem, but in general, the central limit theorem is making claims about equal-sized samples, but that's not due to the central limit theorem. And then the last two, the sample means will approximately follow a normal distribution, and then the sample means will approximately follow a t-distribution. So the central limit theorem, you'll remember, tells us about the distribution of the sample means, and it tells us that it will be approximately normal. The t-distribution, this is another really powerful idea, but this is not told to us by the central limit theorem. We use the t-distribution in cases, which is the most common case, which is when we don't know the population standard deviation. Because we substitute the sample standard deviation in for the population standard deviation, it introduces an extra source of variability that the t-distribution accounts for. But the central limit theorem is telling us about the distribution of the sample means. And like we simulated in class, it follows an approximately normal distribution. Okay, so that's a mouthful. Question 3, you take repeated samples of sample size 50 from a population and plot the sample means. Which statement best explains what you expect to see? So this is the same sample size as the last question. So we're asked about what we would expect to see with repeated samples. So yeah, this is very similar to the last one, but it asks for a little bit more. Here we'd expect the histogram definitely doesn't look like the population because we're looking at this distribution of sample means. It'll look roughly normal with the same spread as the population. So this is also not true. We know the spread will be much tighter because extreme events are much less likely to happen with sample means. The histogram will be normal with less spread than the population, so that looks like a good candidate for a correct answer. And then the histogram will be normal only if the population is normal. So this is, maybe I would quibble a little bit with the writing of this question. We need to be a little bit careful. We're making a claim about it being approximately normal with less spread than the population. That's what the central limit theorem claims, and what we see when we do these kinds of simulations, like we did in class. So here, the general idea is sort of what I've spoken already. We could say something like, let's say extreme values are less common than in the population, which I don't know if that completely answers the explanation here, but this at least gives some intuition for why it's not quite as spread out. So you could also say normal due to the central limit theorem. Okay, so that's at least a ballpark correct answer. All right, so then question 4, a researcher is testing whether a job training program impacts earnings. We've collected data showing that that increases in earnings after the program have a sample mean of 450 and a sample standard error of 200. So then we're asked some questions here. Which of the following correctly describes the sampling distribution of the sample means under the null hypothesis of no effect? So here we have a null hypothesis of zero change in earnings after the job training program. So I'm just going to draw a little picture here. I think these are helpful when trying to answer these questions. You can definitely answer them without a picture, but these are helpful. So here we have a null hypothesis, and we're not told anything about the sample size, so we're going to assume that it's large enough. So it's going to be approximately normal. But we actually aren't told anything about the population standard deviation. All we're told is the standard error. So this is not, because we have two sources of variation, one from the sample mean and one from the sample standard deviation, this is actually going to be a t distribution. We know that because we don't know the population standard deviation. Okay, and then we have the sample mean somewhere out here. So this is x bar equals 450. Okay, so which of these following correctly describes the sampling distribution of the sample means under the null hypothesis of no effect? Okay, so nice. So we know it's not normal, so we can rule out the first two. And then we know it does follow a t-distribution because we're only given the standard error of the sample. And then we're asked which one of these last two is correct. Short answer is both are correct. The way I've set this figure up, we're centering the sampling distribution on the null hypothesis and then asking like how far away from that zero is x bar. But mathematically, identically, we could center the t-distribution on the sample mean if we wish to. I'm not going to draw it here, but in the background, you could think of sort of a symmetric test to this one, which would center the t-distribution on the x-bar. Okay, so both of these would be correct in my book. So then for B, the p-value for this test is 0.028. Which statement most correctly explains what this p-value means? So to graph the p-value a little bit, we have 450, and p-value tells us the probability in the tails more extreme than 450. So we need to look both above and below the null hypothesis. So this is actually negative 450, and we can graph in the tail. So which statement most correctly explains what this p-value means? So let's just say what this p-value means before we look at the options. So here we're saying if the null hypothesis is true, so if there actually were no effect of the job training, what's the probability that we would see something as extreme as what we do see? So the probability of seeing something as extreme given that there is no effect. So let's look through here. There's a 2% chance that the job training program had no effect. Well, this is not the right way to think about p-values. There's a 2.8% chance that the sample mean difference is 450. Also, this is I'm not really sure how you would think about these exactly, but this is not the right way to think about a p-value. Option 3, if the job training program truly had no effect. Okay, so this is in the ballpark already. So we're saying we're in the world of there being no effect. We'd observe a difference of 450 or more extreme, 2%, 2.8% of the time. So this looks like it would be a correct answer. And then the probability that our conclusion is wrong is 2.8%. That's not really a way of thinking about a p-value. So this is the correct answer here. All right, so then question 5. A researcher is testing a null hypothesis that average incomes in the county are equal to $50,000. The sample mean is $56,000, and the sample standard deviation is $2,000. So the researcher has decided in advance to reject the null hypothesis if it lies at least 3 standard errors away from the sample mean. So the first question is, use a figure of the probability density function of the sampling distribution to show the confidence interval the researcher has conducted for this test. So all we have to do here, let's just set up a normal distribution. So we know, at least if the sample size is large enough, that the center, that this thing will be approximately normal. Except we're actually not given the population, so this is going to be approximately t. So this is a t distribution. Okay, so then the way I set these kinds of tests in this class is to center it on the null. But like I mentioned up here, you could center it either on the sample mean or on the null, and it's mathematically equivalent, as we've talked about. So here we have 50,000, it's our null, and then each standard error is 2,000. So I'm going to set up 3 of these. So in the positive direction, that's 56,000. And then in the opposite direction, we have 1, 2, 3, we have 44,000. Okay, so this is our confidence interval. Okay, so nice. So this would answer the first part. And then for part B, write down the values of the upper and lower bounds of this confidence interval. I should make one note here. You could equivalently center the t-distribution on the sampling mean, the sample mean, and that would give you another location to set the confidence intervals, and that would be mathematically identical. So here, and that would actually give you 2 different possible answers. So here, the confidence interval, the way I've written it, is 44,000 to 56,000. But you could equivalently write it as a plus or minus, so it would be let's see, 56,500, and then plus or minus 6,000. I'm not going to do that math here, but this would be another way of writing out the confidence interval. Okay, so for part C, using this confidence interval, is the researcher able to reject the null hypothesis of an average income of $50,000? Well, to test this, all we have to do is write in where x bar is. And it turns out x bar is right here, just larger than the upper bound of the confidence interval. So we reject the null hypothesis. And if you wanted to make a conclusion here, you could say, we are very confident. If you had a p-value, you'd say that here, that the average income is not 50,000. Okay, so I think we'll leave it here. I will see you in the next one.